Okay, so this is a summary lecture on uh, an intro to compressible flows. Okay, so we're gonna start on compressible flows, and I'm gonna give you an introduction into compressible flows, but a very summarized version of it. Okay, so what are the important formulas for incompressible flow? Important formulas. Okay, so number one, we have the speed of sound. Okay, so sound travels through any medium, whether it's solid, liquid, or gas, and it has a certain speed. Okay, and it is derived theoretically to be c equals the square root of k RT. There's a whole derivation in the full lecture, but we will not go through that. What we are interested in is taking this result. Okay, so the speed of sound depends on the material property of air. Okay, the universal gas constant. So this will be a fixed number, and the temperature of the gas, okay, or the temperature of the fluid. Mostly we're dealing with gases because that is a compressible fluid. So this is determined by what gas you use, whether it's nitrogen, whether it's air or some other type of gas, but mostly we'll be dealing with air. So this has a value of 1.4, okay, for air, and for ideal gases. So mostly throughout this course, it'll be 1.4. Now, this is a constant, and if we keep this as 1.4, this is a constant. So that means the only thing that's the speed of sound depends on is temperature. Okay, so that means if you want to calculate the speed of sound, the only thing that you need is temperature, assuming that this is air. Yeah, which is always the case in this course. Okay, so remember this. If you want the speed of sound, you need temperature. If you want the speed of sound, you need temperature. If you want the speed of sound, you need temperature. That's all you need. And this formula, of course. Okay, the next formula that you need to know is Mach number. Okay, so this is a number which gives you a rough idea of velocity of the gas, so how fast the gas is moving. And you can see that this is the velocity of the gas, okay, so the bulk fluid motion of the gas, as a ratio of the speed of sound. Okay, yeah, so that's it. Mach number is a dimensionless number which indicates the speed of the gas. Okay, so from the Mach number, we have different classifications of the compressible flow. So let's take a look. So we have classifications, and there are three broad categories of uh, compressible flows. Number one is subsonic. Number two is sonic, and number three is supersonic. Okay, so let's take a look at the names first. Let's start with sonic. Okay, so m equals to 1. Sonic. What does sonic mean? Sonic means related to sound. And in here, it means related to the speed of sound. Now let's take a look at what happens at m equals to 1 using this formula. Okay, so let's write down the formula. And then we replace m with 1. Okay, so this is a sonic condition. When m is 1, I move c to the other side, I will get this. So v equals to c. What does this mean? This means that the velocity of the gas is equal to the speed of sound. Here, take note, this v is velocity of gas. Then this one is speed of sound. So that means the gas is traveling exactly at the speed of sound. Okay, so that's why we call this the sonic condition, because the velocity is exactly traveling at the speed of sound. Okay, so m equals to 1 gives the sonic condition, or we call it the sonic condition. Now, let's take a look at the name of the other two categories. So here we have subsonic and here supersonic. What does sub mean? The prefix sub means below. Okay. On the other hand, the prefix super means above. Okay, so sub means below, super means above. Why? Why are they given this name? Because subsonic means the velocity is less than the speed of sound. On the other hand, supersonic means the velocity of the gas is above the speed of sound. Okay, so you can do a similar derivation. So let's say, when m is less than 1, okay, when m is less than 1, So V over C is less than 1. And then you rearrange this, it will show you, see, V is less than C. So this is subsonic. Whereas M is greater than 1, V over C is greater than 1, and so V is greater than C. So this is supersonic. See, the velocity is greater than the speed of sound, whereas for subsonic, the velocity is less than the speed of sound. So that's how we get these three categories of compressible flows. So subsonic, sonic, and supersonic. Yeah. Okay. The next important formula is this. So this has a couple of names. You can call this the ideal gas law, or in this course, we will more commonly refer it as the equation of state. Okay, so it's ideal gas law because, well, this applies to ideal gases. And why do we call it equation of state? Because these states refer to the state properties of the gas. So I'm talking about pressure and temperature and density. Okay, so that's why it's called equation of state. The next formula that you should know is the entropy formula. Okay, so there are a couple of entropy versions of this entropy formula. Some of them expressed as in terms of density, some of them expressed as in terms of the velocity, but I think the most commonly used is in terms of temperature and pressure. Okay, so we have a gas. Okay, what's the story behind this entropy change? We have a gas undergoing some uh, entropy change, correct? From state 1 to state 2. That's what this 1 and 2 means. 1 is state 1 and 2 is state 2. Okay, it undergoes a process from state 1 to state 2, and then in that process there's an entropy change, right? If you want to calculate the entropy change of the process starting from state 1 and going to state 2, well, that can be calculated by taking the temperatures at state 1 and state 2 and the pressures at state 1 and state 2 and then putting it into this formula to find the entropy change. Okay, so that's the entropy change formula using the state variables. Okay, now we need to look at some important definitions. So we have some definitions here. So, what is the meaning of isentropic? Isentropic means okay. So isentropic means constant entropy. Okay, the isen part of this word means constant. Okay, so constant entropy. Yeah, entropic means entropy. Okay, so constant entropy, or in other words, there's no change in entropy. So we have a process. If we describe it as isentropic, okay, we have an isentropic process which leads a gas from state 1 to state 2. And since it's described as isentropic, the entropy at state 1 is equal to the entropy at state 2, okay, because there's no entropy change. Okay, so that's what isentropic means. And there are conditions to give rise to an isentropic process. Okay, so number one, the process must be reversible. Okay, so reversible means there's no irreversibilities. Okay? Irreversibilities are things that can cause energy losses. So, for example, friction or shocks. Okay, and number two, it must be adiabatic. So adiabatic means there's no heat transfer. There's no heat being injected into the gas, and there's no heat being taken out or extracted out of the gas. Okay, so these two conditions must be satisfied in order for the process to be isentropic. The next definition that you need to know is a bit lengthy, but it's called okay. Hold on. Okay, so the full name is called local isentropic stagnation state, but the short name is called stagnation state. Okay, so if I say stagnation state, I'm referring to local isentropic stagnation state. Okay. So let me show you our flow process. So this line represents a flow. We have 3 state points here. So state 1, state 2, and state 3. Okay, so each of them has their own static conditions. So let me show you what I mean. Okay, so we have a flow here of fluid, right? And then at each point of flow is some state, right? We have state 1, state 2, and state 3, right? So let's take a look at the name of this thing. What does local here mean? Local, the word local here means occurring at some point. So let's focus on point 1. So some point in the flow, right? So yeah, that's what local means. The local isentropic stagnation state, sorry, the word local means some point in flow. Okay, for example, I just take this random point 1, right? Uh, each point in the flow can be taken, can undergo an isentropic process. Okay, can undergo an isentropic process, which will lead it to its corresponding local isentropic stagnation state. So let me draw you this stagnation state first. Here, this dashed line will go to this point labeled as 0, 1. Okay, and this 0, 1 is the isentropic stagnation state, or the local isentropic stagnation state. Sorry, let me just put the word local here. And its properties, okay, the properties are P01, Rho01, T01, S01, V01, and yeah, V01 is just 0. Okay, so this is a flow, and then I take out 3 random points, so point 1, point 2, and point 3. Yeah. So point 1 is just some point and flow. It's a random point and flow, and it has static conditions, P1, Rho1, T1, S1, V1. Okay. So static, the word static comes from the word state. Okay, state. Okay. So it has these conditions, pressure, density, temperature, entropy, and velocity, because this is a moving fluid, so it has some velocity. But each point, in theory, can be brought to its local isentropic stagnation state. Now, the local isentropic stagnation state is a point of 0 velocity. Okay, it's a point of 0 velocity when some point in the flow is being isentropically decelerated into the point of 0 velocity. Okay, so initially at some velocity v1, right? But then if we let it undergo an isentropic deceleration, okay, which is this dashed line, this is a isentropic flow. Then it will reach a point of 0 velocity called the local isentropic stagnation state, right? It's called local because we're talking about a certain point, and that point we're talking about is point 1. Okay, so that's why it's called local. Isentropic because it is brought to this point by an isentropic process, so that's why it's called isentropic. Stagnation, okay, the word stagnation means 0 velocity. Okay, so that's why there's the word stagnation, and then state, because this is a certain state in a flow process. Okay, so that's the definition of a local isentropic stagnation state. It is a point, okay, a point in a flow can be brought to its local isentropic stagnation state by an isentropic deceleration. Okay, so this stagnation state has its own set of properties, right? Instead of P1 is P01, instead of Rho1 is Rho01, instead of T1 is T01. So the not indicates stagnation. Okay? Not indicates stagnation. Now, realize this, that we take the point 1, and we brought it to 0, 1 through an isentropic process, right? And remember what we said, isentropic means no entropy change. Now, that being said, since there's no entropy change, S1 must be equals to S0, 1. Okay, because they're connected by an isentropic process. Okay, likewise, you can do the same thing for point 2 and point 3, right? You can use an isentropic process and then bring it to its corresponding stagnation state. And likewise for 3, you can use an isentropic process and bring it to its corresponding stagnation state. Okay, so yeah, every point can in a compressible flow can be brought to its corresponding stagnation state. Now, here's what you need to know. For an isentropic flow, there are what I like to call condition ratio relations, okay, or property ratio relations, okay, property ratio relations. For example, this and this and this. Okay, so you know at each point of the flow there is some, there's some pressure, there's some temperature, there's some density, and you know that at each point of the flow, okay, at each point of the flow, it can be brought to its local isentropic stagnation state, okay, namely P naught, T naught, and rho naught. Now, there is a relationship between the stagnation condition and its static condition. Okay, there is a relationship between the stagnation condition and its corresponding static conditions, and that relationship is given by this set of formulas here. So, for example, to relate the static condition to its stagnation condition, it's given by this formula. Then for temperature, it's this formula. Then for density, it is this formula. Of course, you don't have to memorize this because you can bring it to the exam with you in a cheat sheet or get it from some reference book. But what is the important thing to note about this? So the important thing to note is that if you want to calculate, let's say, P01, what you need is P1, right? If you want to know what's rho01, then you need rho1. And if you want to know T01, and then you need to know T1. And vice versa. If you want to know P01, then you need P1. If you want to know T01, then you need T1. Okay. What's the other important thing from this set of formulas? Well, take a look at the right-hand side of each equation here. What do you see are the variables in here? Well, first of the variables I can see is K, right? K appears throughout each of these formulas. Okay, but remember what I said, throughout most of this course, we will just be dealing with K equals to 1.4, which is air. Okay, so we don't need to care about K, we can treat it as a constant. The other variable that you see in the right-hand side of these equations is M, the Mach number. Okay, the Mach number. Okay, you see, there's no other variable other than M. Okay, if we treat K as a constant, then the only thing that these ratios depend on is the Mach number. Okay, so let me just highlight to you. So here's the Mach number, here's the Mach number, here's the Mach number. What does this mean? This means that if you want to calculate, let's say, the stagnation pressure, there are two things you need. Okay, let's say you want this. Okay, so this is question mark. There are two things you need. You need the pressure, the static pressure, and the Mach number. Okay, what else? So let's go to the next one. Let's say you don't know what's the stagnation temperature, right? So what do you need? You need the static temperature and the Mach number. Then the next one, okay? Let's say now we don't know what's the static density. Okay, so what do we need? We need the stagnation density and we need the Mach number. What do you see is common throughout? We always need the Mach number. See, we always need the Mach number, the Mach number, the Mach number, and some other condition to help us. Okay, so for example, in the first two we need the static pressure, static temperature, but in the last one we need the stagnation density. Okay, but the point is that everything throughout needs a condition and a Mach number. That's why Mach number is so important in in the top here. Okay, why I list out as an important for us, because you always need to calculate Mach number in order to access some condition. Okay, in order to calculate some condition. Okay, so that's the importance of Mach number. Okay, so yeah, that's all I have to say about this. Okay, we have another reference state besides the local stagnation state. Another reference state that we will use is a critical condition. Okay, so let me just write this down using a typing because I'm a bit too lazy to write this out. Okay, so what is the definition of the critical condition? The definition of critical condition is the state to which the flow is accelerated or decelerated isentropically until it reaches m is equal to 1. So the sonic condition. Okay, so when the velocity of the fluid is exactly the speed of sound, right? So it could be, you could have a gas and it could be below the speed of sound, so you need to accelerate it to Mach number equal to 1. Or you can have a gas whose speed is greater than the speed of sound, so you need to decelerate it down to the Mach number equal to 1. Okay, so either way, okay, you do this through an isentropic acceleration or deceleration until m reaches the 1, and that state now is called the critical state or the critical condition, right? So how do we denote the properties of the critical state? Okay, so we denote properties, we denote its properties with an asterisk or a star. Okay, so for example, its temperature, its critical temperature, critical pressure, critical area, critical density, and the critical velocity. Okay, so okay, let me just write this down first. Okay, so here are some notes about isentropic flow. Okay, so for isentropic flow, we talked about just now, we have no irreversibilities and adiabatic. So that covers the first 2 points. So we talked about that just now. No entropy change, so that's what isentropic means by definition. And then property variation is only due to area variation. So the area I'm talking about is the cross-section area of the pipe, right? Because we have some flowing gas, it goes through a pipe, then the only way that properties change is because the area of the pipe changes. So this is related for isentropic flow. And then, sorry, MA2 4000. 2, which is the course code of this course, nozzles are isentropic. Okay, so what are nozzles? Nozzles, you can think of nozzles as varying area pipes. Okay, so it could be converging nozzle, it can be diverging nozzle, but as long as you see a pipe which changes in cross-section area, that would be a nozzle. Yeah. So whenever you see nozzles in this course, you can treat it as isentropic. We won't deal with a case where it's a nozzle and let's say, for example, heat is being extracted or heat is being injected into the varying area nozzle. It's a bit too complicated for this course. So yeah, any nozzles you see in this course is confined to being isentropic. Okay, now I claim that property variation is only due to area variation. This doesn't make intuitive sense, right? So we need to delve into the math of this idea. So how does velocity change due to area variation? Okay, so don't forget, every property is connected to Mach number. Okay, this is what we talked about just now, right? From here. Okay, every property is connected to Mach number, and Mach number is controlled by velocity. So the question is, how does velocity how is velocity influenced by the area of the pipe? Okay, that's what we're going to talk about here. So there is a derivation behind this equation that I'm about to write. So let me write down the equation. So dv over v is equal to minus dA over A. Okay, 1 over 1 minus m squared. Okay, so I'm not going to derive this equation, but take it to be true. Okay, there is a derivation behind this, but we're not interested in that. What this helps us is connect v to A. See, v to A. Okay, so there are a few things that I want to write. So note, if dA is positive, then area is increasing. Okay, increasing means increasing in the direction of the flow. Then if dA is negative, then the area is decreasing. Okay, again, decreasing in the direction of flow. Then if dA equals to 0, then this is a stationary point. Okay, so let's just look at how what these three mean first. So dA equals to positive. So let's say the fluid flows this way through a pipe, right? So this is a constant area pipe. But what does it mean for the area to be increasing in the direction of the flow? Okay, so the direction of flow is rightwards. Then if the area increases, then it will look like this. Okay, let me make it clear. Like that. See, the cross section gets bigger and bigger. Okay, so that's what it means by dA is positive. The cross section area is increasing in the direction of flow. Again, let's say the flow is moving rightwards. What does it mean if the flow is, sorry, the cross section area is decreasing in the direction of flow? Then it will look like this. So this is the nozzle, right? So initially cross section area is big. Then after that, as the flow moves along, then it becomes small. Okay. Then what does it look like if it's a stationary point? So if the flow is like this, then stationary point would look like this, right? Here, at this location is where dA is equal to 0. So that's the stationary point. Okay, now we also need to look at the velocity variation. So if dV is positive, then the fluid is accelerating. So I'm not going to write the full thing. Then if dV is negative, then it is decelerating. Then if dV is equal to 0, it's traveling at a constant speed. So constant speed. So no acceleration, no deceleration. Okay, so yeah, if dV is positive, then it's accelerating, so it's moving faster. Mach number is increasing. If dV is negative, then it's decelerating, so Mach number is dropping. And then dV equals 0 means it's moving at a constant speed. So let's look at what happens to this equation when it is subsonic. In other words, when Mach number is less than 1. So let me pull out that equation again. So remember this equation? Now, let's take a look at what happens when Mach number is less than 1. If Mach number is less than 1, okay, for example, just as an example, okay, just as an example, let's say this is 0.1 squared, right? Then this will be 1 minus 0.01, which is 1 over, say, 0.99, right? Okay, but the point is that you'll notice that if m is less than 1, then you notice that this term here, okay, let me write that down again, 1 over m squared. If m is less than 1, then this bracket underneath will always be positive, okay? You can give it some thought, but then it's true, okay? You plug in any m which is less than 1, it's always positive underneath. The thing that I highlighted, this will always be positive, okay? So let's replace it with a positive sign. Okay, so this whole thing is also positive, right? This is positive, so we don't really need to care about it. And then at the end of the day, this whole right-hand side is negative, right? Because of this negative, this positive. So the entire sign of the right-hand side is negative. Okay, so what does this mean? Oh, sorry. Okay, so we don't really need to care about this because this is positive, right? Now, what does this mean? I'm gonna write this down. Okay, so if dA is negative, dV is positive. dA is positive, dV is negative. Right? Take a look at this side. If dA is positive, then negative and positive will give me negative, right? Which means that my dV is negative. So that means for subsonic flow, okay, for subsonic flow, as area decreases, velocity increases. Okay. On the other hand, okay, if you do the opposite thing, if you let dA be negative, so let's see what happens. So if this is negative, negative will give me positive, right? So now dV is positive, right? dV positive means that the flow is accelerating. Okay, so in summary, we have these two effects. When dA is negative, dV is positive. When dA is positive, dV is negative. What does this mean qualitatively? Okay, the first line means when the cross-section area decreases, velocity increases. The second line says when cross-section area increases, the velocity decreases. This makes sense, right? At least from an intuitive standpoint. For subsonic flow, so remember this is for subsonic flow. As the cross-section area decreases, we expect that the gas moves faster. Whereas when the cross-section area increases, then the gas is more spread out and it will move slower. Okay, so this is in line with our intuition from incompressible fluids. Okay, so nothing to worry much about here, for at least for subsonic flow. So take note that this is for subsonic flow. But what about supersonic flow? Okay, so this is a different story. Okay, so when m is greater than 1, okay, when m is greater than 1, this m squared will be also greater than 1, right? M squared will be greater than 1, then this whole denominator will be negative. So if you don't believe me, you can plug in an example. So let's say example m is equals to 2, right? So let's say this is 2. So this whole thing will be negative, right? Because 1 minus 4 is negative 3. So this will be negative. Okay? My point is, if m is greater than 1, then the denominator here will always be negative. Right? Take a look at this. Negative, negative should give me positive, right? So at the end, this whole thing here will become positive. Now, we have to consider the different cases again. So now let's copy this down and investigate what happens. So when dA is negative, okay, when dA is negative, what happens? Okay, when this is negative, dV is negative. Then what happens when dA is positive? When this is positive, then dV is also positive. Okay, now what does this mean from a qualitative standpoint? When the area of the nozzle is decreasing, the velocity of the nozzle is decreasing. When the area of the nozzle is increasing, the velocity of the gas, okay, the velocity of the gas is also increasing, right? This doesn't make intuitive sense from what we know, right? We know that if we squeeze a, okay, from an intuitive standpoint, right, using our intuition, if we squeeze a pipe, okay, we constrict the pipe, we expect that it will go faster, right, for the same flow rate. And if we expand the pipe, then it will go slower for the same flow rate. However, supersonic flow will beat our intuition. Okay, supersonic flow is counterintuitive. Supersonic flow is counterintuitive. So when we decrease the area, the velocity slows down, right? The fluid slows down. When we increase the area, the gas moves faster. Okay, so supersonic flow is a very counterintuitive process. We have no intuition as humans, right? As humans, we do not have any intuition with supersonic flow because for the most part, everything we know, okay, or most things we know, happen at uh sonic, sorry, at very low speeds, like low gas speeds. So we have very little intuition about supersonic flow, right? So that's why I take note. Don't try to use intuition to suss out the behavior of supersonic flow. Yeah, because you get this counterintuitive behavior. Okay. Yeah. Okay. So in summary, okay, so let me write down a summary. Okay, so let me investigate now sonic flow. So when m is equal to 1. When m is equal to 1, we have dv over v is equal to minus dA over A. Okay, when we need to rearrange this first. Okay, we need to rearrange this equation first. Okay, so I'm gonna move this to the other side. So this will be 1 minus m squared dv over v minus dA over A. Right, now I'm gonna substitute m equals to 1 here. 1. You notice that this becomes 0, right? So we have 0 equals to minus dA over A, and then dA is equals to 0. Right. So what does this tell us? Okay, so this tells us, right? Remember we set the condition to m equals to 1. M equals to 1 is also known as the critical condition. Critical condition. When the speed of sound matches, sorry, when the velocity of the fluid is the speed of sound. Critical condition. So we don't only call it the sonic condition, we also call it the critical condition. So after rearranging this equation, when we solve m equals to 1, we notice that the result is dA equals to 0. This means that in order for critical condition to occur, dA must be equal to 0. In other words, that the critical condition only occurs when dA equals to 0 for isentropic flow. Okay, critical condition only occurs when dA equals to 0 for an isentropic flow. So let's say we have a converging diverging nozzle. Right? This is converging, diverging, converging, diverging. Right? dA equals to 0 occurs here at the throat. So this is what you call the throat. Right? It's the point of minimum area, minimum cross-section area here. The only place where the critical condition occurs is at this point, the stationary point of area, otherwise known as the throat. Okay. However, this is a necessary, okay, necessary but insufficient. This is a necessary but insufficient condition. What does that mean? Necessary means in order for critical condition to occur, it needs to be occurring at the throat. However, just because you're at the throat, it doesn't mean it's always critical condition. Okay, so let me say it again. At the throat, it may or may not be critical condition. Okay, at the throat, it may or may not be the critical condition. But if you are told that a nozzle has a point of critical condition, it must necessarily occur at the throat. So in order for a nozzle to have a point of critical condition, it must occur at the throat. It must occur at the throat. However, just because you're at the throat, it may or may not be at critical condition. Okay, it could be it could be subsonic at the throat. Okay, it doesn't have to necessarily be m equals to 1. However, if you have a convergent diverging nozzle, m equals to 1 must occur at the throat. Okay, the point where m equals to 1 occurs must occur at the throat. That's what it means to be a necessary but insufficient condition. In order for critical condition to occur, it must occur at the throat. However, just because you're at the throat, it doesn't mean critical condition has occurred. Okay? For all you know, m could be, let's say, 0.7 at the throat. However, for m equals to 1 to occur, it must occur at the throat. Okay? So think about it a few more times. It's a bit confusing, but yeah, that's what it means. Yeah. Okay. So let me give you a summary of what we just talked about. Okay? So here's a summary of what we talked about just now. Okay, so you don't have to exactly know all these derivations, but here's a summary of what you need to know. Okay, so for subsonic flow, converging nozzle, okay, subsonic flow is intuitive. Okay, it follows our intuition about incompressible flow. So for subsonic flow, converging nozzle accelerates flow, diverging nozzle decelerates flow. Right? This just it follows the behavior of incompressible fluids. Okay. However, supersonic flow is counterintuitive. So a converging nozzle decelerates the flow, a diverging nozzle accelerates the flow. Yeah. Okay. So this is counterintuitive. Converging nozzle decelerates the flow, diverging nozzle accelerates the flow. Okay. So yeah, that's all I had to comment as an introduction to isentropic flow and compressible flows. Okay. So see you next time. Oh, uh, If you found this summary lecture to be helpful, you can donate me on PayPal. Yeah, it'll be very helpful. Thank you.